We have here our next topic, which is the distribution factor KD. So we already finished the KP or the pitch factor. So distribution factor is defined as the EMF with we now go to equation of induced EMF in an alternator. So we will let Z or Z be the number of conductors or coil sides in series per phase. So we have two coil sides in one conductor, di ba? it is equal to 2T, or where T is the number of coils or turns per phase. So remember, one turn or coil has two sides. P is the number of poles, F is the frequency of induced EMF in Hertz, flux is the flux per pole in Webers. So KD, or distribution factor, KP, pitch or coil span factor, cosine alpha divided by 2. KF is the form factor, 1.11. So that is form, not from. If an EMF is assumed sinusoidal, so N is the rotor speed in RPM. So in one revolution of rotor, such that in 60 over N second, each stator conductor is cut by a flux P Webers. So we will take the derivative and then you will get the average EMF induced per conductor. Flux NP over 60. Now we know that our frequency is equal to number of pole multiplied by the speed divided by 120, or N is equal to 120 F over P. Substituting this value of N above, we get average EMF per conductor is equal to flux P over 60 times 120 F over P is equal to 2F flux in volt. If there are Z conductors in series per phase, then average EMF per phase is equal to 2F flux Z volt. So that is for frequency, flux, number of turn in volt. So RMS value of EMF per phase is equal to 1.11 times 4 F flux T is equal to 4.44 frequency flux number of turns. So this would have been the actual value of the induced EMF voltage if all the coils are in phase, where number 1, full pitch, and number 2, concentrated or bunch in one slot instead of being distributed in several slots under poles. But this not being so, the actual available voltage is reduced in the ratio of these two factors. So this is the actual available voltage per phase now. 4.44 kpkd flux multiplied by frequency times number of turns. So if the alternator is star connected, as is usually the case, then line voltage is square root of 3 times the phase voltage. In star. So iba naman sa delta, kasi yung delta, yung current ang mag-i-square root of 3. Effect of harmonics on pitch and distribution factors. So what is an harmonic? So harmonics are unwanted higher frequencies which superimposed on the fundamental waveform, creating a distorted wave pattern. In an AC circuit, a resistance behaves in exactly the same way as it is thus in a DC circuit. So thus, that is, the current flowing through the resistance is proportional to the voltage across it. So if the short pitch angle or chording angle is alpha in degrees, electrical, so iba yung electrical degrees at saka yung mechanical degrees. So mechanical degrees in a motor refers to the rotation of the shaft. So one revolution of the shaft equals to 360 mechanical degrees. So in electrical degrees naman, in a motor has to do with the magnetic position of the rotor. So one transition from north to south to north again equals to 360 degrees. So one rotation, for example, we have a two-pole, north and south. So north, south, south, north. So in a mechanical degrees, we have 360 degrees for this one. And also in electrical, for two-pole, okay, electrical degrees, we have also 360 degrees. Because we only have north, south, north. But if, so this has a sine wave of like this one. If we have a four-pole, north, south, north, south, mechanical, we have 360 degrees. But in electrical, for every north, south, north, we have 360. So how many north, south, north here? We have north, south, north. So we have 360 now here. Another north, south, north, north, south, north. So we have another 360 degrees. So in four-pole, we have 360 times 2. That is 720 electrical degrees. And we have 360 degrees mechanical naman. If you have 6 poles, magbilang ka lang ng north, south, north. So that is 360 degrees. North, south, 180. South, north, another 180. So magiging north, south, north, ganon. So that will be, balin niya, yan, this one. So for harmonics, we have, if for third harmonic, we have 3 alpha. For fifth harmonic, 5 alpha, and so on. Pitch factor, Kp or Kc is equal to cosine alpha 2 for the fundamental. Cosine 3 alpha over 2 for the third harmonic. Cosine 5 alpha over 2 for the fifth harmonic. So similarly, the distribution factor is also different for different harmonics. So its value becomes Kd sine m beta over 2, where your n is the order of the harmonic. So diba we solve our beta a while ago equal to 180 all over n. So this n here will be the order of harmonic. For fundamental, n is equal to 1. We have a subscript here to denote fundamental, Kd1. For third harmonic, we have Kd3. For fifth harmonic, Kd5. So same formula, ang pagkakaiba lang ay yung n. Yung 180 over n. Yung value ng beta. Frequencies also change. If fundamental frequency is 50 Hz, so F1 denotes the fundamental is equal to 50 Hz. Then other frequencies are, for third harmonic, we have F3 is equal to 3 times 50. Fifth harmonic, F5 is equal to 5 times 50, etc. So if you have seventh harmonic, F7 is equal to 7 times 50. So this is the example of a sine wave of different harmonics. So yung red, this one, non-sinusoidal waveform. Yung green, first harmonic, we have our fundamental, yung pure sine wave. Third harmonic, blue, we have this one, 1, 2, 3. Yung fifth harmonic naman, 1, 2, 3, 4, 5. 5 yung one complete sine wave. Yung 3 naman, third harmonic, 3 yung complete sine wave. Okay? Example, an alternator has 18 slots per pole and the first coil lies in slots 1 to 16. Calculate the pitch factor for fundamental, third harmonic, fifth, and seventh harmonic. So, first we will solve the coil span. We will begin counting at 2. Okay, so if we count 2 until 16, so that is 16 minus 1, we have 15 slots. And the total is 18 slots. So we will have a short pitch, or which falls short by 3 slots. 18 minus 15 is 3 slots. Our alpha is equal to 180 times 3 over 18. Our pitch factor, 3 over 18 is equal to 30 degrees. And then solving for the fundamental, short pitch factor is equal to cosine 30 over 2. That is cosine 15 degrees, 0.966. For the third harmonic, we have cosine 3 times 30 over 2. That is 0.707. Short pitch factor at fifth harmonic is cosine 5 times 30 divided by 2. We have 0.259. At seventh harmonic, cosine 7 times 30 over 2, that is 0.259. Example, a 3-phase 16-pole alternator has a star-connected winding with 144 slots and 10 conductors per slot. The flux per pole is 0.03 Weber, sinusoidally distributed, and the speed is 375 RPM. Find the frequency RPM and the phase and the line EMF. Assume full pitch coil. So list all the given parameters given in the problem. We have an alternator which is in 3-phase. So the symbol for phase and flux is the same. Huwag kayong malito dito. So this is 3-phase. It is connected in star or in Y. Other term for star connection is Y. And also we have 10 conductors per slot. Number of pole is 16. And also the slots is 144. The flux per pole is 0.03 Weber. The speed is 375 RPM. Solved for the frequency, the phase voltage, and the line voltage. So for our formula, it is given in per phase. E phase is equal to 4.44 multiplied by the pitch factor times the distribution factor times the frequency, the flux per pole, and the number of turns. So in the problem, since Kp is not given, assume that Kp is unity. We can solve the distribution factor, sine mb over 2 divided by m sine beta over 2. So beta is equal to 180 degrees divided by slots per pole. So 180 divided by 144, which is slots and number of pole is 16. You will get 20 degrees electrical. M is equal to the slots per pole per phase. You have 144 and number of pole is 16 and the number of phase is 3. So you will get 3. Solving now your KD, it will be equal to 0.9598. For the frequency, we have our formula, number of poles multiplied by the speed divided by 120. So you will get 50 Hertz. For the number of turns, 2 turn is equal to 1 conductor. So number of turn, remember that the number of conductors given in the problem is in 3 phase. While we use E phase, so we must convert your number of turn 3 phase into single phase. So we can solve number of turns equal to number of conductors divided by 2. From our formula, 2T is equal to Z. Z is the number of conductors. So we have 144 slots times 10 conductors per slot divided by 2. So number of turns in 3 phase is 720 turns. If we get the number of turns in single phase or per phase, is T phase is equal to 720 divided by 3. That is equal to 240 turns. So solving now your E phase, we have 4.44 times 1. Our KP is 1. KD is 0.9598 times the frequency 50. The flux per pole 0.03 and the number of turns equal to 240. So E phase is equal to 1534.144 volts. Solving for the line voltage of the alternator, we get square root of 3 multiplied by 1534.144, that is equal to 2657.216 volts. So this is the schematic or circuit diagram of a Y connected alternator. So this one, I assume that you already discussed this in your circuits 2 in polyphase. Okay, so I will not discuss this anymore further. So this is your ground or neutral, this broken line here, and you have your 3 lines, line A, B, and C. So the line-to-line voltage or the E line are lines EAB. You remember EAB, EBC, ECA for the positive sequence. So this is, since this is connected to line B and line C, so this is EBC. This is EAC, and the other one is EAB. So EAB. While your phase voltages EA, EB, and EC, they are connected to a one line and to a ground. So ito yung E phase natin. For line B ay phase B. This is EB. This is EC or EA, and the last one is EC, this one. EA from this point to the ground, EA, EB, and EC. So the voltage here, line to line, is 2657.216. So iba pa yung mga angles niyan from line AB, line BC, and line CA. So I will not discuss any further kasi tapos nyo na yan sa polyphase subject nyo. I don't know kung last sem. So that's it. We will have another example.